So Darren's been working with Tim Axelrod at the University of Arizona on the LSST project, Large Synoptic Survey Telescope, and in using ReadyNet, which is a distributed data system out of Vanderbilt, I believe, for data management, data storage. And I think with that, we've got quite a large number of attendees. And Darren should be good to go. Everyone should log on to atconference.com with the participant code that was on the symposium website. And I believe Darren's ready to go with the slides, so take it away, Darren.
Okay, thank you, Nancy. Yeah, so as Nancy mentioned, I'll be talking about this collaboration effort. I think what I want to cover in this talk is I just want to highlight some of the interesting aspects, in particular, of the ReadyNet infrastructure and the underlying technology, which is deemed LSTOR is the actual name of the server software. And ReadyNet itself is like an implementation of that. And so I'm just going to cover some of the broad goals that we set out to achieve with this effort, and in particular about LSST itself. And then, like I said, I want to cover some of these unique features of the ReadyNet system and of LSTOR. I'll mention briefly some of the particular aspects of the work that we did in the advanced user support collaboration. And then just a little time on possible future directions, and conclude with that. So I just want to mention, Nancy mentioned Vanderbilt University. Those were our core collaborators: Alan Tackett, Bobby Brown, Santiago, I won't try to say his last name, Matthew Binkley. These are all at the Advanced Computing Center for Research and Education at Vanderbilt. And then here, mostly the LSST team that I collaborated with consists of Mike Freeman, Ray Plant, Greg Doss here at NCSA, part of the data management team of LSST. So the LSST project itself, a new telescope, a large synoptic sky survey telescope, has the world's largest camera, 3.2 gigapixel camera. And the goal of this telescope is to do wide field survey astronomy. And so, yeah, did anybody say data? I mean, they're going to be generating an unbelievable amount of data with this project. Now, that unbelievable amount of data becomes more and more believable as we get closer. I mean, it's not as pie in the sky as it was 5-6 years ago when they first conceived of this, but it's still a big challenge. So just a few particulars about the data challenge we're faced with. So this camera is capable essentially of generating around 30 terabytes in a single observing night of raw, and that's just raw data. There's various projections of how much generated data products, secondary data products, and so forth that'll cascade off of that. And I think it's an ongoing balancing act to decide, how much data they're going to generate. The sky's the limit, really. And then they have an additional challenge. This is not something we did a lot of work on in this collaboration, but they're doing a long-haul data transfer testing from the telescope itself. And I put a quote in here from the LSST website, and I think this really characterizes their approach to the data on this project. They're basically saying that they're going to provide the data to at least the U.S. and Chilean scientific communities with no proprietary period. So they want a really quick data turnover. It's an explicitly stated philosophy of their project to to generate more science by making the data open, available, and I think it's really a key to their project that the better job they do of that, they believe the more science they'll enable. So this kind of effort is a key aspect of the LSST project. And also, I mean, so they explicitly state the no proprietary period for U.S. and Chilean, but they also are committed to providing the data, open data sets to collaborators worldwide as well. So, as part of this collaboration, we're assisting in evaluating different technologies. LSST is still in an R&D mode. It's sort of in a waning R&D mode, I believe. I don't have the exact timeline, but they haven't adopted ReadyNet or LSTOR yet, but it's under evaluation. So it's a very similar technology as iRods, perhaps more mature. It's been around longer, and the commonality is that we have a global namespace for distributed storage architecture. So have several replicas that can all live underneath a single logical name. A lot of these concepts are very familiar to people that have worked in data management with the Globus Replica Location Service, iRods, SRB, things like that. Now, one of the unique aspects of ReadyNet is that they have basically deployed a testbed architecture. ReadyNet itself is a deployment of this LSTOR service on a distributed network that has buy-in from many collaborators. The last bullet there, ReadyNet itself is a collaborative cross-institutional collection of LSTOR IBP depots. So IBP is the Internet Backplane Protocol, which I'll talk about more. Here's a pretty picture from the ReadyNet website, just to give a visual of what ReadyNet is. And again, I should mention that it's an implementation of LSTOR. So I'll try to move along here. So this is the bit I really wanted to talk about, is to talk about some of the key features of LSTOR. LSTOR itself stands for logistical storage. Bits are bits, so it's the idea of abstracting away storage technologies and creating an even playing field for bringing in these logistical. So logistical, I mean, they're drawing off the analogy to military logistics, and using many different underlying storage architectures, but having the same at the bit level. So it's built on the Internet Backplane Protocol. Another interesting feature is their extended Xnode technology that they've developed, which is an XML-based metadata system that's very similar to a Unix inode. One of the really interesting aspects to me was the use of a distributed database using Apache Cassandra to handle metadata. I know that metadata is kind of the nemesis of a parallel file system, and I think this is kind of an interesting approach that it'd be interesting to see how this pans out and how it scales. And so the ReadyNet infrastructure is where they store large data, and in ReadyNet itself, the servers are made up of these Internet Backplane Protocol servers. And then finally, one of the key features I wanted to mention is they have a policy system for managing data, for managing replicas, and you name it. It's a user-driven policy engine and very flexible. This is from the LSTOR website. basically their definition of logistical networking, kind of their the premise for doing this project. It's in the slides. I'll skip ahead, just the time. Now here's some pretty slides, the ones that I borrowed from Vanderbilt researchers. So the thing I basically wanted to show you on this slide was their depiction of where the Internet Backplane Protocol lives in the broader context of Internet technology. And to mention the concepts of, against this protocol, one of the unique aspects is that they're able to create allocations that have a time limit. So they create a time-based allocation against this protocol, and then they manage those allocations higher up in the stack of LSTOR. So the ReadyNet infrastructure is made up of what they call storage depots, which are IVP servers. And this gives a little depiction of that. They essentially the only commonality is that they've run this server process. They can be different storage disk, whatever, JBOD disks, tape archives, and so forth. So another slide for more details of the Internet backplane. I think I'll skip ahead in the interest of time. So this slide gives a depiction of another interesting feature of this technology. What they're able to do is they're able to take the files, say, that are being stored and abstract them at the block level. So against these depots, they can, say, stripe files across different resources or replicate them. And this is all mapped into the Xnode metadata system. So in the interest of performance, say, on example C on this slide, you can see that how the metadata would block up for a file that was striped across depots. So you can actually have sort of a RAID-type striping of files across resources, so that when the files are requested, the bits can fly in parallel from different resources and gain performance, transfer performance. And then on the other side of that equation, you can gain fault tolerance and from replication. And an aspect of this that LSST is interested in is replication tied to geographic locale, so that researchers that are interested in particular pieces of the LSST dataset can have them locally with high availability. So this is a little bit more about the Xnode metadata. I think, again, this is in there for completeness. I think I'll skip ahead. I think I mentioned what I wanted to about this, that basically it sits in between the LSTOR server and the Internet backplane protocol. And it's their analogy of an inode that allows them to do all these interesting things like striping and RAID type of emulation of the storage. Just another depiction of this feature of RAID 5 example of how they could stripe a file across storage depots. Now, another interesting feature of this, another interesting aspect of this feature is that one of their biggest clients, I believe, is a TV station that's based near Vanderbilt, and they have the archive of all their in the field video data, and so they've come up with some unique approaches to help them serve up that data more efficiently. And I think this is one example where they're able to actually change the layout of the file through their metadata system, while still maintaining mappings to the traditional file view for various applications that would expect that and so forth. And they're able to get quite a bit better performance out of by eliminating disk leaks and so forth. So they're really working at the block level, at kind of a lower level than what I've seen in other types of file management systems. Now, another nice feature of this system is the distributed metadata. And again, I mentioned that as something that is kind of an Achilles heel of parallel file systems in general. So this system uses the Cassandra, Apache Cassandra database, which is a NoSQL database. It's symmetric, so every node in this database is identical, and there's no parent node or any single point of failure. And it uses a distributed hash table for lookups, which is, I think, an order login type of lookup system, and it has they like to call it tunable consistency, so you can dial in the amount of consistency that you may need. So an example would be that if you let's see, I think I actually have an example on another slide. So here, running short on time, so I'm going to speed through a couple of these. This just reiterates the order login lookup. It's a depiction of the distributed hash table used in Cassandra. Go back to that again. Okay, so I think that's all I need to say about Cassandra. I'll try to move forward here and see if I can get through all my slides. So the key features of LStore are this logistical storage approach, trying to abstract at the block level and provide new capabilities of striping and performance enhancements. Distributing the metadata so that I think in practice what happens is when you create a depot with the Internet Backplane Protocol server, you also have like possibly a separate disk partition that could store metadata. That could be a node of the distributed database metadata. Now, the particular work that we did with the collaboration was to take the LSST data sets that they generate in each of their data challenges, which they store in archival storage in the tape archive here at NCSA, and integrate that into ReadyNet. So we wanted to do a read-only pull from our mass storage system and have that be map onto this global namespace of files that is their data set. So in mass store itself, they're stored in tarballs, so we had to come up with a way to bring the metadata online into ReadyNet or into LStore, and then have the staging happen behind the scenes when a file request comes in. So we did that, the granularity of these tarballs that they already had in mass storage. Now, one of the cool upcoming features that we're testing is a fuse mount. So the capability of having a file system mount to this ReadyNet architecture, or to in the future it would be to an LSST implementation of ReadyNet. So it would be possible for researchers to have a directory mount of all of the data in the LSST project. Another future direction that we're looking at is exploring the use of LStore policies to manage replicas and to provide a good data caching policy. So, to come up, one aspect of that is actually come up with good algorithms. Another is to be able to implement them so that they can have the right data sets available for scientists in the right locations. Now, to take this a step further, this is something I've speculated about, would be to move into a feature set where, similar to Dropbox, where not only do you have a file system mount, but you also have data versioning, or because that's one of the neat features that I think of Dropbox, is that you, for free, get like essentially a versioning system for your files. I thought I had this in a slide, but I'll just mention it. There's a open source attempt at Dropbox called Sparkle Share, and they based the file system clients on a Git repository. So you're essentially marrying version control with directories. And I think this could really have a big benefit to researchers that take this data from the LSST project, say, in a read-only type of Dropbox mount, and then this mount could be served up to their local depot, their local IBP depot, and then they could also have a space where they could write data that they derive data sets that they generate, could be pushed back to the LSST community and so forth. So this, to me, seems like has a lot of potential. So just as LSTOR and ReadyNet, I think the takeaway is that the interesting underlying technologies that LSTOR is deployed on, like the IBP, the Xnodes, Cassandra. I'd mention it's not as mature of a project as something like iRods. It doesn't have you go to their website, the source code is there. It's not even licensed, I don't think. So it's open source, but it's not formally open source. The documentation's lagging a little bit, but it's not as mature of a project. One of the other interesting aspects is that they sort of leverage this ReadyNet deployment as a way to entice researchers to join the project. I think that's a big benefit is that, and they manage that. So it's managed by the Vanderbilt team. You basically provide some servers, and they drive the servers for you. They update the software and keep things rolled out and keep it online and so forth. And I think that's something that's attractive to a lot of teams, where they don't have to dedicate a grad student or 2 or 3 or whatever to keeping the servers updated and digging through documentation and so forth. And I think that some of the new features like the Fuse interface really do have the possibility of satisfying some of these very ambitious data sharing goals of the LST project. And finally, I just have a slide here with some of the links to some of the technologies that I just mentioned. And thank you very much.
Darren, thank you very much for a very interesting talk. We're going to put the slides up on the symposium website. I think next month we'll try to do that before so that people can have them if they want to skip ahead or follow along or things like that. So we'll definitely have those up there. So, okay, we've got some questions coming in. Ian Stokes-Reese is asking, what are used for ACL identities?
Did you say APL?
ACL.
ACL. Oh, access control list.
Yeah.
That's digging in a little deeper than I think that I got. So I don't have an answer for that offhand. I don't know.
Fine. Amit Sharazia asks whether iRods will be used also for LSST, or right now LSST is in an evaluation mode.
Yes, they are in evaluation mode. That's they're evaluating iRods as well. And so this presentation was more emphasized the ReadyNet aspects because that's what I helped out with. But yes, they are still evaluating, and iRods is still on the table.
Yeah, thanks. Ian asks again about a good talk that he's heard recently on OODT, and sounds like there's some overlap at the metadata and file manager catalog level.
Okay, that's interesting. I hadn't come across that one myself, but I'll check that out.
And Ralph Roskis asks if there's any charge for licensing.
Not that I know of. I kind of had the same question, and the code to stand up an IVP server is freely available on their website. It's just really sparsely documented right now. I believe it's an open source project, but I haven't been able to find an explicit statement of that. And by the time I had thought about that question, it was a little late to ask them. So, I think it's open source.
Yeah, very good. Ian mentions that the OODT code is from JPL, just in case you were going to follow up there, Dan.
Oh, okay. Thanks.
And John Kaz asked about whether you were able to pull an individual file from a tar, or did you have to stage the whole tarball?
Well, okay, yeah. So the first cut was we basically, once it's in the LStore system, you can pull individual files. They wanted the file level access in their distributed data system. But on mass storage, it's in tarball. So the way that we did it was, yes, we did pull an entire tarball. So if someone came through the LStore interface, once all the metadata is loaded, and they requested one file that lives inside of tarball X, then the entire contents of tarball X would be imported currently.
Yep, thanks. I know on HPSS we used to use an htar command to get, I think, a single file out of a tarball, but I think that was HPSS specific, not general.
Yeah, they have their own system for managing a tape archive. So to actually have a tape archive behind one of the IVP servers is something that they're working on, and I think they've already done. But this is where we're basically trying to kind of kludge the tape system at NCSA together with the ReadyNet system, and that was just the simplest solution at the time.
Okay, we've got a couple of more questions in about 1 more minute. Ian asks whether the GFFS team is looking at what ReadyNet and LStore are doing. Probably more of a question for Andrew Grimshaw, I would think. It's about the Exceed, some of the new Exceed architecture that's coming out. I don't know if you're familiar with GFFS at all, Darren?
A little bit, yeah. I can't answer that question, but I would be interested in that answer as well.
Okay, maybe something we ought to follow up on as staff members.
Sure.
Let's see. So Ralph asks about would the Vanderbilt group charge to manage someone else's servers for them?
That's a good question. I don't know. I mean, they don't have an explicit policy as far as this goes. I think it's kind of informal at this point, and I don't think they're charging for service or any, for ReadyNet collaborators. I think it's kind of a mutual benefit type of relationship where the more collaborators they have, the more support for their research they get. I think it's that kind of setup right now.
Okay, a final question. Amit Chirazia asks if the compute and storage sites are identified for LSST, or if that's still in evaluation as well.
I believe it's still in evaluation. I know that that NCSA has been everything I know is that they've chosen Champaign, Illinois, NCSA as their archive site, as like main archive site. So that would mean that an entire replica of all the LSS data would live here, and then would be disseminated through other means to other research institutions. So, and I believe the LSST project also is planning on purchasing all of their own hardware. So, so they would have their own compute compute capabilities, clusters, archive storage, and then would deploy whatever technology they decide to onto that. So they won't be trying to leverage existing, say, Exceed resources or something like that. It will be kind of in-house, but I think the plan is to base it at NCSA.
Very good, Darren. Thank you very much for being our very first symposium speaker.
Okay.